So I'm going to talk about some joint work. So everything I talk about is joint with Paul Seymour. A lot of it with Maria Czernovsky, and then parts also with Sophie Sperkel, all at Princeton. So this is going to be part of. So Paul and Maria and I have been writing a long sequence of papers. I think it's up to 14 now on this sort of larger topic, and I'm going to sort of do a slice through them and tell you a sort of a piece of it. So obviously I can't talk about the whole thing, but I'll try and focus, and I'll talk about some results and try and give you a hint of the proof. So the whole sequence is on graphs of large chromatic number, and the fundamental question is, so what can we say about the structure of a graph with a large chromatic number? Okay, well that's sort of a big question. Let's specialize it slightly. What can we say about the local structure? So what can we say about the local structure of a graph with a large chromatic number? Okay, and what do I mean by local structure? I mean the induced subgraphs. So specifically, induced subgraphs. Okay, so induced subgraphs, in other words, they're specified by their vertex sets. You pick some vertices and you have to take all the edges among them. So if you have a complete graph, every induced subgraph is a complete graph. Okay, right, now, the first thing you might guess, just naively, of course, is that you might, when you first see this, and this is a kind of a standard question to throw at undergraduates, if you have large chromatic number, maybe that means that you have a large clique. Okay, so that's sort of the naive thing you might guess. And of course, that's long known not to be true. Actually, so here's sort of the Tutte connection. Tutte in 1947 came up with examples of graphs, so constructed graphs, triangle-free graphs with large chromatic number. Okay, so there exist triangle-free graphs with large chi. Okay, so of course there are now lots of constructions, and in fact there's a later result of Erdős, and again it's now an easy result, but it was an early application of the probabilistic method. More than that, there exist graphs with large chi and large girth. So not only no triangles, not even any short cycles. Okay. Right, so we can't hope for, we can't guarantee anything too dense, so you have to modify the question slightly. So, okay, so large chi implies, well, either a large clique or, and then something else. Okay, so you say either I have a large clique or I get something else. You have to allow for a large clique, because if your initial graph is just a giant complete graph, then the only things you get are cliques. Okay, so everything in this talk focuses around questions of this form. If I have large chromatic number, then do I get either a large clique or something from some particular class of graphs? Okay, so what's the first question you could ask of this form? Well, you could say, what if chromatic number is bigger than clique number? So, okay, so now I need to define a couple of things. So they've been defined a few times already, I think. But so a hole is an induced cycle of length at least 4. So triangles don't count. And an antihole is, well, it's a hole in the complementary graph, so it's the complement of a hole. So a hole in the complement. Okay. Right. Okay, and then the very famous strong perfect graph theorem. So Chudnovsky, Robertson, Seymour, Thomas in 2006. So says that if you have no odd hole and no odd antihole, so odd hole means induced cycle of odd length, and an odd antihole is the complement of an odd hole. If you have no odd hole and no odd antihole, then the chromatic number and the clique number are the same. Let me write this slightly just in the same format I'm writing everything else. So chromatic number, I don't know, I'll write it the usual way. So no odd hole, no odd antihole implies chromatic number is equal to clique number. Okay, so that's sort of a very famous result, important result, a beautiful one. Okay. But what if chromatic number is much bigger than clique number? Okay, so this says as soon as chromatic number goes above clique number, then you get certain things, or something from a certain family of things. And by the way, I mean, this is a minimal family. You can check that holes, okay, odd holes, clique number is 2, chromatic number is 3, and there's a similar statement for antiholes, odd antiholes. But what if chromatic number, maybe I'll use my height and try to use more board. What if chromatic number is much bigger than clique number? I guess I'll put an extra bigger. Okay. What, do we get more? Okay. And there's a beautiful paper of Gyárfás from 1986 or 1987, let's guess 87, where he raises a whole lot of questions of this type. So he says, if chromatic number is much bigger than clique number, do you get this graph or this graph? And in particular, there are 3 well-known ones involving cycles. And cycles of holes are what I'm going to concentrate on in this talk. So the first one was chi large implies large clique or odd hole. Second one was, okay, so what's happening here? So you look at the strong perfect graph theorem or strong perfect graph conjecture as it was, and that says if the chromatic number is large, you get a large clique or an odd hole or an odd antihole. Okay, this says, okay, can I dispense with antiholes? So can I just ask for an odd hole? Okay. By the way, odd holes, so holes are quite sparse objects. I mean, there's just a few edges scattered in a big set. Antiholes are very dense objects, so there's just a few edges missing from a big set. So it's sparse objects generally we're looking for. Okay. So the second one was chi large implies large clique or long hole. And then the third one was chi large implies large clique or, okay, so he conjectured odd hole, he conjectured long hole, and then he put them together and said, okay, what about, here's even more of a challenge, what about, so now long odd sounds better than odd long. Long odd hole. Okay, so those were the 3 Gyárfás conjectures. Okay, so those have been proved over the last 2 or 3 years. But before I get to that, I'll try and go kind of roughly chronologically. So there was another conjecture. Do I have a date? There was another conjecture of Calais and Mechelin that came from topological origins. And so everything here, I mean, odd hole, there's a theory to do with even holes as well. Calais and Mechelin asked about holes mod 3. So So they conjectured that if you have no induced cycle of length 0 mod 3, so including triangles now, then your chromatic number should be bounded. Okay, so it kind of pushes you away a bit from even versus odd. It kind of mod 3, residues mod 3. So Bonamy, Sharby, and Thomas say, so actually they proved this that, well, the other way around, if G has no triangle and no hole of length 0 mod 3, then chi of G is bounded, so is the most sum constant. Okay. And this was sort of quite an important paper because it was the first paper that pushed things away from even versus odd, and there was some good ideas in there. Okay. Actually, before I get into stating more things, let me say, when you have these sorts of questions, I mean, the strong perfect graph theorem, so it's a beautiful set of techniques, and it's sort of looking for some very precise things. So that the argument, which I don't know well enough to summarize, but it says if you have a minimal counterexample, then you can decompose it in one of a certain set of ways. There's certain sets of nice things that you can find in the graph. Okay, and you get a precise result. So you have to kind of look for precise things to get a precise result somehow. Okay, these questions, okay, you're not going to get something so precise. You're not likely to get a precise bound just because these graph classes are much less structured. I mean, you know, are you going to have a structural theory of graphs with no hole of length more than 10 to the 10? Well, it's probably not going to be very pretty to get something precise. So you have to have something slightly looser. So you can still hope for some structural information, but you're not going to get a very precise decomposition type result. And the other thing is you're not going to get these precise numbers. So you know, the numbers are going to be much larger. Again, I'll comment on that in a bit. Okay, so let me carry on and say what do we know. So the first conjecture Paul and I proved a couple of 2 or 3 years ago. So we showed that if G has no odd hole, then chromatic number is at most 2 to the 2 to Clique number of G plus 1. Okay, so it's a doubly exponential bound. Probably not sharp. Actually, I'm pretty convinced that there should be a singly exponential bound. There's only one place in our proof where the bound bumps up from singly exponential to doubly exponential, and it feels like if you kind of come along with just a slightly better way of doing things, then maybe it'll drop down to singly exponential. But the proof is we did it. It's not clear how you'd improve beyond that. Okay, I'll comment for lower bounds. There's a tiny lower bound Clique number to the 1 point something small. I mean, it's kind of pathetically small lower bound. So there's a huge numerical gap. Again, none of these results do we have anything close to a good function here, but that's not the point for the moment. The first thing is actually to show there is a function at all. Okay, so that was the first one. The second one, so this is with Maria. I'll just say that's true. And I won't write down what the function is. And then the third one came out in, I think, December. So that's with Sophie Sperkel as well. So in other words, it's the complete set. So every time we added a letter, we got a stronger theorem. I guess these two are incomparable, but so 3 is true. Okay. So finally, we got all the 3 Gyárfás conjectures. The third one was tough, actually. It took a long time to come out. It was very annoying. Somehow controlling length and parity was difficult, and we needed some new ideas for that. Okay. Now we can do a bit more. So let me mention 2 more results. Right. So current state of the art. So So this is me and Paul. So for every t, chi large implies, right, so large clique, or holes of all residues mod t. Okay, so not just even or odd or mod 3, whatever. So this contains all the previous results, very much builds on the techniques that that we developed in those papers, with some new stuff too. And the second theorem, this is from a year or two ago again, chi large implies, so this was, I mean, thinking about what if you exclude triangles. So chi large implies either you get a triangle or holes of 10 to the 10 consecutive lengths. So, I mean, any constant length you want. So you can get arbitrarily long intervals of holes, is the point. Okay. So this somehow is, this is really pretty strong. It also suggests somehow that the precise sort of structure, mod, whatever, isn't so important. I mean, this in some sense says that, okay, if I look at the, it's enough to forbid holes with, a set of holes with bounded gaps is really what it says. So you get a long interval of holes. So the missing hole lengths, somewhere there's a big jump where you have lots of holes. Okay, I'll just say, so we conjecture that this should be true with large clique instead of triangle. Okay, that probably won't come from our techniques as they currently stand. We use, so in this proof, so this is a long hard proof, and we use triangle free a lot. I mean, there's some sort of special things that happen when you're triangle free. We exploit them heavily. So it needs new ideas. Okay. Right. So that's what I'm going to what I'm talking about. So my plan is that I'm going to try and sketch, very, very roughly sketch, the proof of this result, the residues mod t. Okay. As a warm-up, let me sketch a weak version of this result with Maria. So warm-up. So I'll prove the following result, that large chi implies large clique or long hole, but I'll throw in something else, or C5. So throw in one additional cycle length. Okay, so one short cycle to make things a bit easier. Okay. Right. So always in these things, argue by induction on K, which is the clique number. Okay, and start with K equals 1. K equals 1 is nice and easy. So the base case is trivial, yeah. Okay, so I should have said, I'm going to be informal in a certain set of ways, a kind of precise set of ways. So long means you choose how long it is. So I'm kind of trying not to, so you can state all this properly with all the correct quantifiers in place. So what I should really say here is, for every choice of clique size, every choice of long, so for all K and L, there exists a chromatic number, so there exists a K, capital K, such that chromatic number greater than K implies either you get a clique on K vertices or a hole of length at least L or C5. So that's a formally correct statement of that. Okay, so always I'm going to mean that you make choices of what you want on the right, and then if the chromatic number is large enough, you get that. Okay, but to save time, I'm not going to keep stating that, unless it's unclear, in which case, please do ask. Thank you. Okay. So implicitly, there are always sort of functions. Implicitly, there are always explicit functions in the background. Okay, so let's argue by induction on k equals the Clique number. So let's assume we're doing the inductive step. So we can certainly assume that for every vertex, its neighborhood has bounded chromatic number, okay, because the Clique number is smaller. So we're assuming we have a graph with, so G with huge chromatic number. The inductive step tells us that neighborhoods have small chromatic number. So for all x, the neighborhood of x has small chromatic number by induction. Okay. And now, well, we look at what happens locally. So it could be that, I mean, the natural, so maybe actually, let me draw a picture first. So what's the most natural way to look for a long cycle? So here's the sort of the idea that if you sort of sit and think about it for 5 minutes, then this is the first idea you hit on. You say, okay, I'll start at some vertex. I'll go out layer by layer. And after a bit, I'm going to hit a layer with large chromatic number. Okay, if the graph has huge chromatic number, there's some layer with chromatic number at least half the chromatic number of the whole graph. Okay, so I go down until I hit a layer with, so the whole graph has huge chromatic number, so there's a layer with fairly huge chromatic number. And what am I going to do? So I'll start the layer just above it. I'll go down here. I'll go for a walk. And then I'll come back up again. And then maybe join up somewhere in the top. Maybe I get to the top, maybe I don't. So maybe it meets up there. But as long as I've gone for a reasonable length of walk down here, I've got a nice long hole. Okay, so that's got a very natural way to do it, and that's what you do, but then you run into some obstacles. Okay, and the real obstacle is that, well, if I go for a walk, great, I've got my nice long walk, I can certainly do that, and I'll show you the argument in a second. The trouble is, it might be I get to here, and now I've gone for a walk, it's time to head home, and unfortunately, I've already seen all the vertices in this layer. So I've kind of blocked off my return route. Okay, and that's always a problem. So that's always a problem you have to get around. Okay, so let's start just sort of slightly more locally. Let's just start with, so you need something to control that. So let's start just very small, let's start at radius 2. So first, suppose there exists a vertex x such that the 2 ball, so everything within distance 2 around x has large chromatic number. So here we are, there's x, there's the neighborhood of x, and then here's the second neighborhood of x. Okay. Right. Now, the neighborhood of x has small chromatic number by induction, so I can take a coloring. Okay. And if I look at each vertex class, so each vertex class has a set of children. One of those sets of children must have large chromatic number, because this has small chromatic number, this whole thing has, we're assuming it has very large. I'll make this very large. I'm not quite sure why I need the word very, but anyway, just to emphasize it's very large. Very large, but not huge, not necessarily huge. So, and again, you can write down explicit functions here, but I'm trying to avoid lots of technical detail. So the sort of strength of an additive indicates, so huge is always bigger than very large is always bigger than large is always bigger than quite large. Okay. Right, so one of these vertex classes has children with large chromatic number. Okay, so I'll just restrict that vertex class. So here we are, there's one vertex class, so it's a nice stable set, and I'll just keep its children here, so its children have large chromatic number. Okay. Now, this is a set down here with large chromatic number. So by induction, either we get one of the things we want, or we have a maximal size clique. So here we are. This is a clique on k vertices. Okay. So, right. Let me draw that clique a bit bigger. Now we're almost done. Actually, I'll get rid of everything except the clique. That's all we actually need. So this is kk. Now let's let's pick a vertex in here that has as many neighbors as possible in there. Okay, so here we are. Here's a vertex with as many neighbors as possible. So maximum number of neighbors. Not going to be adjacent to everything, otherwise we have a bigger clique, and then we're happy. So there's something that's not covered. Okay, and that something, well, has a neighbor up here somewhere. So what do we know? We know that this vertex is not adjacent to that one. And this vertex, well, it has one neighbor that's not a neighbor of this, so it can't be adjacent to all the other neighbors. Let me put another vertex in there. It can't be adjacent to all of these. Otherwise, we chose a vertex with the maximum number of neighbors to begin with, so there must be some vertex down here that's not adjacent to. And now we've got a C5 because I join up like so, and I've found a C5. Okay, so that's my C5. Okay. So otherwise, every two-ball, okay, let me rescale a bit now. Every two-ball has small chi. There's no two-ball with very large chi. So let's just kind of step back a bit, rescale our functions. So two-balls have small chi. Okay. And that turns out to be good enough to make this strategy work. Okay. So how do we do it? So actually, maybe I'll just do it from this picture. Oh, maybe I'll do it from this picture that I just erased. Okay, maybe black is better as well. Okay, so here's the base. Okay. So I'm going to start at any point in the layer just above the base. Okay, so here we are. There's my vertex. I'll call this x1. It's got some children down here. Children have small chromatic number, so the non-neighbors have large chromatic number. The non-neighbors in the base have large chromatic number. If I delete the neighbors of x1, what's left falls into some components. One of these components at least has large chromatic number. Okay, not quite as large as the whole thing perhaps, but still very large. Okay, so this one has large chromatic number. Okay, so this is an argument due to Gyárfás, by the way. So it's called, we call this Gyárfás paths. So we're sort of just walking into the graph step by step. So here we are, x1, neighbors of x1. There's some large chromatic number component of the non-neighbors of x1. And there's some vertex adjacent to x1 that has a neighbor in there. So I'll pick such a vertex, call it x2. Okay, and now I'm going to sort of forget all the rest of it. I'm just going to focus on this one component. Okay, and I'm going to do the same thing again. So from x2, I'm going to say if I delete the neighbors of x2, it might break up this component, but one of the components I get will have large chromatic number, say here, and I can choose an x3 that has neighbors in there. And I'll do the same thing again. I'll go walk step by step into the graph. After a bit, what do I end up with? So I'll redraw it. So here we are. And here's the point. I have this path. None of these vertices, x1 up to, let's say, xl, have neighbors in this big chi set. But maybe this last one does. Well, actually, and this last one does. Okay, so now all I want to do is just get back up to the top. So I've walked for a specified distance, whatever I want for the whole length. And now I need to get back up and connect again. And here's where we use the fact that second neighborhoods have small chromatic number. Okay, so if I look at everything in the second neighborhoods or the two balls around the piece of path that I've got so far, well, that all has small chromatic number. So the two ball around each of these vertices has small chromatic number. So the union of the two balls has small chromatic number. So there's only a small chromatic number piece of this that's within distance 2 of any vertex on that path. So in particular, there's a vertex here that's distance at least 3 from x1 up to xl. Okay, right. Well, that has a parent somewhere. And that parent is distance at least 2 from x1 up to xl. In particular, it doesn't have any neighbors on the path. Okay, so what I'll do, I'll just connect this up, and I'll walk along here. Now, so take a shortest path inside here. Now, this vertex might have neighbors on that path, but that's fine. I'll just take a shortcut, as long as it doesn't have any neighbors in this initial segment. Okay, and the crucial thing is we were able to choose an initial segment of exactly the length we wanted. Okay, so it's some fixed length. Everything within distance 2 has bounded chi, so we can escape from its second neighborhood and come up. And we connect up in the top any way whatsoever. It doesn't matter how. Okay, good. So we get a long cycle. So, okay, sort of end of proof symbol. Okay. Okay, so the rest of the time, I'm going to spend my time talking about that result. And I'm going to give you an extremely rough sketch of one or two of the ideas. This is strange. I'm used to boards that go up and down. And this is... So if I start leaning over, that'll be why. Okay. Right, so... So hints or proof of residues mod T. Okay, so that's the result I'm talking about. Okay, so once again, so as usual, induction on K equals the Clique number. And so again, K equals 1 is trivial, so we can assume that, so the base case is trivial. So we can assume that for every vertex x, the neighborhood of x has small, I hope it's clear, I'm being informed when I say the neighborhood of x, I mean the subgraph induced by the neighborhood of x. Okay. Right, now in the in the warm-up argument about long holes, it really split into two cases. So there was one case where locally the chromatic number was large. There was some two-ball with large chromatic number. And then there was another case where locally the chromatic number was small. So every two-ball has small chromatic number, but globally the chromatic number is large. Okay. We're going to do the same thing again, but we're going to have, and this is a common feature of all these proofs, that you end up looking kind of locally and then less locally. So we're just going to split it into 3 this time. So firstly is that there's a two-ball. So I want to do something slightly stronger than that. Okay, so let me make a slightly stronger statement. So first one is every induced subgraph with large chi has a two-ball with large chi. So we're going to split into 3 cases. I'll explain this in a second. So for some small r, every induced subgraph with large chi has an R-ball with large chi, but not true for R minus 1. Okay, so it is small r, at least 3. And the third one is going to be G has huge chi, but every 8 ball, so it's enough to go up to 8, has small chi. Okay, and I claim actually it's enough to handle these three regimes. Okay, so why? So in the previous argument we just said, is there a two-ball with large chi? If there is a two-ball with large chromatic number, then we win. Okay, but that's not going to be enough for us now because it's going to be a multi-step argument and we'll take a two-ball with large chi, okay, but then inside that large chi we'll look for something else and then we'll want the same thing to be true again and there's going to be some iteration. Okay, so let's do the following. Let's look at our graph and say, if there's a subgraph with large chromatic number, but all the two-balls have small chromatic number, I may as well drop to that. Okay, so then I'm in a graph now where it still has pretty large chromatic number, but the two-balls have small chromatic number. Okay, so that's going to be sort of escape from case 1 if that happens. If that's not the case, but I can't do that, then every subgraph with large chromatic number has a two-ball with large chromatic number. Okay, so it says that whenever I take a piece of my graph that has large chromatic number, there's some little local bit where I can see the chromatic number is large. Okay, so that's 1. Now, maybe 2 is not enough. Maybe I have to go out to some slightly larger radius. Okay, so maybe it's 3, 4, 5, 6, 7, 8. Or maybe that's not the case. Maybe I can drop to a subgraph where it's got large chromatic number and all the 8 balls have small chromatic number. So these actually do cover all cases. You have to write down the functions and you have to write it down carefully, but it works. Okay. So I don't want to write down quantifiers and explicit functions. I very much don't want, and you don't want me to either, I claim. Or if I do, you'll wish I hadn't. So. Okay. Right. I'm going to talk about, I won't talk about 2, but it's very much the same ideas as 3 with a bit of a twist. So I'm going to sort of say something about 1, I'll say something about 2. Okay, and let me emphasize, this is, in all these results, this has been an important thing, that some graphs, the chromatic number is locally large in this kind of explicit sense that always every large chi piece, there's a little local piece where you can spot pretty large chi, and sometimes the chromatic number is somehow more diffuse, that locally it's small, but somehow you go to the cloud and it's large. And these sort of 2 classes of graphs seem to behave a little differently. We have to treat them slightly differently. Certainly the arguments are different. Okay, so let's deal with case 1 first. Okay, I'm not going to say much about this case. So actually, I think we first really had to get to grips with 2 balls in the long holes paper. Let's think about 2 balls. So here we are. I've got a graph with large chromatic number. I know there's a 2 ball with large chromatic number. So here we are. Here's my vertex x. Neighborhoods are always small chromatic number by induction. So let's just assume it's a stable set. You can color to do that. Okay. And now, so the children here have large chromatic number. So again, since this has large chromatic number, there must be some 2 ball with large chromatic number. Okay, so I pick a vertex. Second neighborhood has large chromatic number. Let's forget the rest of the base. There we are. Okay. Now, let's call this first one x1, the second one x2. And x2 will have various parents there. And actually, for simplicity, let me stick to the triangle-free case. You have to do a slightly more complicated version of this if you're not triangle-free. Right. What about the second neighborhood out here? So there's sort of two things that could happen, A and B. So somehow the nice thing, so the thing that is more fun, certainly, is when there's a large portion of this second neighborhood that can get back up to x1 without going through neighbors of x2. So every vertex here, there are paths back up to x1, and I'll just look and say, do they go through the neighbor? Can I get up without going through a neighbor of x2? So can I get up through the right-hand side? And if I can, I like that. Okay. Otherwise, almost everything out here goes up through the left-hand side and not through the right-hand side. Okay, this is the nastier case. And I'll just, hard to draw, but I'll just say these vertices, because it's triangle-free, they go up there. Okay, so they can get up that way, but these guys can only get up via neighbors of x2. Okay, so there's two things that can happen, but still, we can carry on at least. So this has large chi, so there's a tubal with large chi. Okay, so here we are, there's a tubal with large chi. And then this has large chi, so there's a tubal with large chi. I can keep going for as long as I want. So I'll keep going for a nice long time. And for every pair, so I get x1, x2, x3, and so on, for every pair, one of these two things, A or B, happens. Okay, and so if you have a collection x1 up to x whatever, and for every pair either A or B happens, naturally you want to apply Ramsey's theorem and assume the same thing always happens. You can, but you have to check that it works, and you can, doing something here doesn't kill you there. You have to sort of check that's true, but it's fine, it works. Okay, so you can assume it's always A or always B. Now, A is a nice case, because because I can draw it, for one thing. But you get something that we call a multi-cover. So here we have x1 up to x r, say, and then some large chromatic base that all of these neighborhoods, so it's in the common second neighborhood of all the x's. And there might be edges between the neighbors, but there are no edges from the x other than to their specific children. Okay, so I'll say that this is a nice case. You can do a lot. You can clean up the picture quite a lot. It's fun. I like the arguments. What you end up building, so you drop to some subset of these columns, of these x's, and you throw away big pieces of the graph. But what you end up finding is a subgraph like this. So it's a induced one subdivision of a complete bipartite graph. So you can see, I'm just drawing K33 with every edge subdivided once there. Okay, so you can find that. And yeah, if you're going to read a piece of it, I'd say that's the most fun bit. This gives you all length, holes of all lengths, 0 mod 1, 2, 3, 4, 5, 6, 7, 8. Well, certainly pretty much all lengths of 0 mod 4, other than maybe 4 cycles. You can also stick on a short odd path if you play around a little bit. So I won't go through the arguments, but I'll say it's very much doable and it's nice. This case is not so nice. You have to sit, you write things down, you stare at it, you kind of find a path that goes through a whole collection of sets, and you write down the definitions, and you check that it really is induced, and it is. And it's painful, but true. So there was pain and there was gain. So I won't try to. I'll just say it works. You just have to look at it very carefully, and things are there. Actually, when we first saw it, when we were doing the long holes paper, we couldn't quite believe it was there for a little bit. At least I didn't, but it was. Okay. Right. So let's go on to case 2. So So I ran a bit long on case 1, so I'll try to speed up. Right, for case 2, there's a kind of nice tool. It's called a grading, or we call it a grading. What's a grading in a graph? So it's just a sequence of sets of vertices. Okay, so it's here we are. So let's say W1 up to WS. It's just a sequence of disjoint sets of vertices. So there's just, that's all it is. It's nothing complicated. Stable grading if each Wi is stable, it's a k-colorable grading if each Wi is k-colorable. Okay, but I'll just talk about stable gradings. Okay, right. So suppose W1 up to WS is a stable grading in G. Okay. There's a Markov chain on board erasers. Okay. Maybe this can go. Yeah, maybe this can go now. Right. So let's also suppose that if I take the chromatic number of the union, it's large. Okay. So this could just come from a coloring. I could just color my entire graph, and I just split it into stable sets. So there's nothing complicated going on, but it could sit somewhere inside the graph. So this may not be the whole graph. It just sits there as a piece. Okay. Now, I claim that. So this is under the assumption that neighborhoods have small chromatic number, which we know by induction, that we can find the following. So we can find an edge and a large chromatic number connected graph, so that one end of the edge has neighbors in that large chi graph. The other end of the edge doesn't. And now here's the useful thing. This is earlier in the grading, and this is later in the grading. Okay. Right. Again, it's not too hard to do. I think if I had 5 more minutes, I'd do it, but I want to move on a bit. Okay. So maybe I'll just say that so that. Yeah, it's a fairly simple M. I hope it's believable. You can find this structure in there. You have to do a little work, but it's not too hard. Okay. So how is this going to be useful? So we have to find our grading from somewhere. So I'll just say that's a claim, and I'll just say it's true. Here's a way to construct a grading. Okay, so I've got a cover. So I'm thinking always, again, this picture, you start from some vertex, you go out in layers. Eventually, you hit a layer with large chromatic number, which I'm denoting by a rectangle. So there are sort of some number of layers up above that. Why don't I do the following? I'll take some ordering of the cover, so of the previous layer. And from the first set in the grading, I'll take the neighbors of this. For the next set, I'll take the neighbors of that. Well, it may have some earlier neighbors, but I'll just take the new neighbors and so on. So I've ordered this as x1, x2, x3, and so on. And wi will be the new neighbors of xi. Okay. So given an ordering of this, I can construct a construct a grading. Now, what do I know about these boxes in the grading? Well, they have small chromatic number because they're all in each one's in the neighborhood of a single vertex. Okay, let's assume they're stable. You can color and drop to one color. Let's just assume they're stable. So we have a stable grading with large, and the whole set has large chromatic number. We know we can find somewhere some edge, and there's a later piece of the graph with large chromatic number, and one end of the edge is adjacent, the other end isn't. Okay, now, why is this useful? Well, this is useful because it's starting to look like a switch. So a switch is an object through which you can run two different paths, and the lengths differ by some predictable amount, in this case by 1. So what could we do? If we think about walking in from here, we could go through here and come up there, or we could go through here and, let me draw it to the other end first. So we could go through here and come up there, or carry on and come up there. Okay, and the good news is that x1 and x2 have no neighbors up here, because it's later boxes in the grading, and we've already taken all their neighbors in these earlier boxes. Okay, so I can do whatever I want in here, and I know that I'm going to be able to get back up as long as I avoid neighbors of these two guys. But you know, x1 and x2, it's safe to come. I've got a nice clean route in, and I can get paths of two different lengths. And look, the way I've drawn it, there's no edge here because this comes after that. Okay, so it looks like we have a nice way to construct a one switch. So again, I can go like that or like that. Okay, but trouble is, so you have to think about what happens up there, but also you have to think about what happens here, and it could well be that x2 is adjacent to this vertex. So you can find this, but we haven't been able to control which of these two vertices comes first. Okay, so you need a bit more argument, and I'll just say bounded clique number is enough to do it. Well, yeah, if you embed it in the argument correctly. So what you really want is an edge like that, so where this vertex is not adjacent to that, and this one, well, it's guaranteed not to be adjacent to that. Okay, so in this picture, we actually want a matching up. Okay, so I'll say you can do that. Okay, it's a slightly more involved version of the argument. Okay, I'm running close to the end of time, so let me kind of just sketch how we use this finally. This is a way to construct a single one switch. Okay, now you hit the problem that kind of, again, recurs throughout this. I can build a one switch. How do I build another one switch and chain them together? So, I mean, this is a nice big piece of graph. I can find a large chromatic number layer. I can walk to that. I can construct another one switch. But I might have to walk an awfully long way, and I might have then seen everything in the layer above, and I cut off my return route again. So I kind of, again, there are obstacles. So you have to find a way of chaining these one switches together in such a way that you can get back at the end. Okay, this is something that, so the Bonomi-Sharby-Thomasé paper, one nice thing from that paper is they found a way to chain two one switches. So that was kind of the key thing in that. They found a way to put two one switches together, and that's enough to get all lengths of 0 mod 3. Okay, so if you have two single bit controls, that's enough. Okay, so let me finish by drawing a picture. So what are we going to do? Well, we're going to be a bit more picky about the order that we take our cover vertices in. So we'll look into the base. The base has huge chromatic number, and inside the base, we take again, one of these layerings. Here's a layer with huge chi, and we're going to use this set to choose an ordering of these. So the ordering we'll take is, the earlier ones in the ordering, so I like vertices that have a neighbor that's close to this, so that's in a high layer in this bottom grading. Inside a layer, I don't care, I'll just put an arbitrary ordering on each layer. So I'll order these vertices. Vertices to the right are earlier, and let's say I've chosen an order inside each layer, higher vertices earlier. Okay, so higher layer wins inside each layer, just pick an arbitrary ordering. Okay, order these vertices, order the parents, by their earliest neighbor here. Okay. Right. And now, for each vertex here, well, I look at its earliest parent, and I get some path up here. That's, if I look at it, I mean, can't control the length exactly, but we can think about the length modulo t. So there's only t possibilities. So one of them must be very popular. So I can assume that this whole graph here, drop to a subgraph where it's connected, has a large chi, and all the paths up via the earliest neighbor have the same length mod t. Okay, I then use this to construct a grading. I build one of these things, so that's later. These have, so they each have an edge up, and they go back somehow, possibly to very different layers. So that the paths might be very different lengths, but they're the same length mod t. And now what have I got? So this really is a switch, because I can, so from here I come in, I can go either up there or up there, and this whole graph doesn't see either that vertex or that vertex. Okay, so I've got this nice big graph here. I could now do the same thing again. So I construct another switch, and then another switch, and another switch. I have to be able to get up again, but there's not very many vertices I need to avoid. I need to avoid going through neighbors of x1, so x1, x2 here, as I've drawn it, whatever I've used there, and a few others. It's just a bounded size set. That's where the 8 balls come in. You have to avoid going through parents of these as well. Okay, but you can build a whole lot of these, chain them together, and then go back up to the top again and join everything up. And that gives you all holes of all lengths, 0 mod t. Okay, that's a very kind of rough sketch, but that's kind of one of the key extra ingredients. Okay, I'll stop there. Thank you.
Thank you. Are there any questions for Alex?
We have to find all ranges of modular t and also log.
So is it possible to?
So your result is you can find all ranges for modular t, and also can you higher the log?
Yes. So and that just actually comes from the statement of the theorem. So if you want a long odd hole, well, you may as well find a hole of length 1,000,001 modulo 2 million, say. So you can tweak to get a long hole of any residue. Yeah.
Any other questions?
So is there anything known about modular 4 or any other integers? Oh no, not modular, the length modular 4.
Well, we get all lengths modulo 4 from this theorem. But more than that, no. I should say we can do 2 holes of consecutive lengths. We can, but we haven't written down because it's a bit messy. 3 consecutive lengths, but that's as long as we can go towards an interval at the moment, as far as we can go towards an interval at the moment.